Hello everyone, today we'll talk about the solution to the problem find if array can be sorted. Let's start with some basics. If you have an array and you're allowed to swap two adjacent elements, then you can swap any two elements within that array, and so you can reorder the array however you want. Because of course to swap two elements that are not adjacent, you will first swap adjacent elements until those elements meet. Then you swap them, and now this left element is on the position of the right element, and then you have to swap the right element back for it to be at this position. And so this part stays the same, those two have been swapped. And if we can swap any two elements, then we can of course reorder the array however we want. In this problem we want to be sorting the whole array, then probably we just want to sort it. That's essentially what bubble sort does, sort the array by just swapping adjacent elements. The second part is that here we cannot just swap any two adjacent elements, we have to make sure that they have the same number of set bits. And the thing to notice here is that if we swap two elements that have the same number of set bits, then the number of set bits at every position in our array doesn't change. And it's obvious, because let's say that those two elements have the same number of set bits. After swapping them, they still have the same number of set bits. That's the same number. And that means that we can separate our array into contiguous subarrays. And each contiguous subarray will have elements that have the same number of set bits. And all those borders are between two elements that do not have the same number of set bits. Our operation cannot change the shapes of those subarrays. So we can swap any two elements within a subarray. So let's say that here we have 6 elements with some bit count. Then we can swap them however we want. We want to make sure that the array can be sorted, or we have to tell if the array can be sorted. So what should we do? Well, we should sort every block and see if the array is finally sorted. Because of course if every block is not sorted, or not every block is sorted, then the whole array is not sorted. So we just have to sort them and hope that that's enough. And we could of course solve this problem like this, by first determining what are those blocks, and then sorting every block separately and seeing if the resulting array is sorted. However, we don't have to actually use a sorting algorithm, and we don't have to then pay the price of having an O of n log n solution, because in order to tell if after sorting all the blocks the array is sorted, we can only look at a subset of elements to determine that. In particular, let's say that this part is already sorted. So what can go wrong on the prefix up to the end of that block? Well, nothing goes wrong here because it's sorted. Nothing went wrong here because we're looking at this block. So the only thing that can go bad is that some pair of elements in the left and in the right side are an inversion. The left element is bigger than the right element. But in order to check if that's the case, well, certainly we only need to keep the maximum, or the last element, so the last element in sorted order, which is the maximum element. The maximum element can be determined in linear time and constant space. So we can, by going through the second block, compare every element in that block with the maximum element from all the blocks that we've seen previously. It will be the maximum element of the previous block, but that doesn't really matter. If after that comparison all the elements here are bigger than the maximum that we've seen in all the previous blocks, then the array after adding this block is still sorted. And of course we have to remember what the maximum element is in that block, such that after the end we can update the maximum on the prefix to be the maximum of all those maxima. And of course we don't care about the situation where this element is bigger than this element, because we can swap them however we want. We only want to compare with the maximum that reaches up to the beginning of the current block. And then we go to the next block, so we're interested in the maximum that reaches up to the beginning of this block that we're looking at. So that gives us a linear time solution. We'll be again going through all the values, remembering the previous value that we've seen, and the two maxima that we remember. The current maximum will be the maximum that is the maximum of all the elements that we've seen, and all max is the maximum over all the elements that are before the current block begins. In order to determine the number of set bits in a number, we can use bit count, in Python. This is a relatively new feature, I think from Python 3.13. So if you don't have that, you can just do string of v and count the character 1 within that string. But bit count is of course faster, so we're happy that we can use it here. And again, if the bit count here is not the same as the previous bit count, then we just remember that the new bit count is equal to the bit count that we see now. And we have to update the maximum over all the prefixes, because now the block has ended, so we have to remember the maximum up to the end of that block. And the failure case is when the value that we're currently looking at is smaller than the maximum up to the beginning of the current block. In that case, we return false. And the current maximum, of course, is just maintaining the current maximum up to the position that we're currently at. At the end, we just return true, because that means that we went through all the blocks, and we never had the situation where an element in the block that we're looking at is smaller than the biggest element from all the previous blocks.